go ahead and get the recording started. All right. Now let's have some fun and talk about some thermodynamics for the last time. So you guys only need to know this information for another 26 hours, and then you're good. You can literally forget about it for the rest of the semester. So, first thing I want to know is...
until finals, of course.
Pretty sure he doesn't cover it on the final, actually.
Really?
Unless he's changed that from the last 3 semesters, yeah.
Well, I mean, I'm just saying, it's just normally sometimes finals covers all, but okay.
Yeah,
if
but
that's...
yeah, the way he's done it, at least the last 4 semesters or whatever, you cover thermo the first few weeks, you have your, like, midterm exam, or in this class for the summer session, it's literally just weekly quizzes, or everyday class quizzes. And then you just never cover thermo from that point forward, because it's just, honestly, it's so different from everything else you do in this class with electricity and magnetism. It doesn't really make sense to, it's almost essential. It's essentially just the most convenient way to fit it in, because you need to fit it in a 100 level class, is just to throw it in with E&M, but it doesn't really make sense to really put them together. So Warchesky started doing it like 2 years ago. He just covers thermo for the first few weeks, midterm exam on just thermo, and then you just never cover it again.
Huh.
So, and then Goolsby Cole stole that idea from Warchesky when he came back from paternity leave, and he's been doing it since.
Okay.
So yeah, 26 more hours of thermo, then you never have to worry about it again. So, let's go ahead and talk about, just a little reminder, what's the first law of thermodynamics again? The first law.
It's delta U equals Q minus the work done by.
Exactly. So we have delta U is equal to Q minus work by. So what is delta U?
Delta U is internal energy, right?
Exactly. And how can we relate delta U to something else that we know that we can measure?
We can use it with isn't there one equation where it's like 3/2 and then moles, the constant, and temperature?
Does anyone want to elaborate what exactly it is? Because you're on the right track. You're just missing one thing.
Don't think. I don't know.
Anyone want to help Azoma out?
I know what she's talking about. It's when you can be related to CV mole NT, but I'm trying to remember the actual name of the process.
Well, it doesn't have to be named. Just like give me the formula.
U equals the CV mole NT, where I believe N would be the mole.
Is it CV, or is it? It's not a heat capacity, is it?
I mean, it can be heat capacity, like the specific one. It depends on if it's constant volume or constant pressure.
Are we just relating it to like the translational kinetic energy?
Yeah, exactly. And so what's the formula for that?
Okay, so it's
Okay.
Yeah.
So it's the degrees of freedom one, isn't it?
Yeah, Michelle, go ahead.
Oh.
Okay. It's the other one. So 1/2 kBT.
Yeah.
Yep. And that's for a single molecule. So then you have to multiply by the total number of molecules.
Okay.
Yep. It's this. So K is equal to 3/2 NKBT. And so then the change in internal energy, delta U, does he actually give it here? No, he doesn't, but essentially delta U is 3/2 NKB delta T. And so then what is Q again?
Do you want the formula or what it actually
Just sort of describe what Q is.
Q is heat energy that can be transferred from one object to the other one through thermal contact.
Yep, exactly. And I'm not really going to ask for a formula in any case because it's sort of a bit more complicated if we have like constant volume or constant pressure and whatnot, and how Q is affected. But the thing is, we just come back to this first law of thermodynamics, and this is what we actually use to understand Q. And then obviously the work done by the gas. How do we get the work done by the gas?
Is it just the area under the curve?
For what? Under what
For-
curve?
Or is the PV curve for pressure and volume?
Yep, exactly. And so how
Yeah.
do we get the area under a curve?
You just calculate pressure times the change in volume.
What if pressure is also changing?
If pressure is also changing, I think you so that would be like a diagonal line, right? So you'd also calculate that change, but it'd be half that value.
What if it's not a linear transformation? Like if it's going something like this, or a curve of some kind?
Wouldn't you just use the inverse of PdV for the work? If I'm saying that correctly.
I'm looking for a keyword here, and
If-
Roger, you
if-
pretty much had it. But go ahead, Michelle.
I think that you would then use like the one for isothermal, right?
I mean, you
So
have
it'd be
your
NRT.
specific.
It would be NRT, a natural log of the volume change.
That would be for constant temperature. But what about for a general case? We don't know anything about it. We just know there's a change in pressure and a change in volume. How do we get the area under any curve?
Is it the integral?
Integral. Yes, there we go.
That's the word.
That's the word I was looking
trying
for.
I knew it had to be I knew what it was. I just couldn't figure out that word.
Yeah, we're going to integrate. Go back to Calc 2 a bit, and we're going to integrate to find the area under a curve. And by integrating, we actually end up getting these specific values that we find here. We have the P delta V, where we have the nRT natural log, or negative NCV delta T, depending on what kind of...
There's a quick question. Do you know where Dr. G could have put up the equation sheet or the formula sheets?
Oh, where I got this?
Mm-hmm.
Yeah. Give me just a moment. So you essentially, it's on Blackboard. You go and open it up. You can find it. You go to courses. It's under course materials, and you have your different classes. You scroll down, and it's in formula sheets.
Gotcha.
So this is the thermo equation sheet, and then you also have your other ones for later in the semester.
Gotcha. Thank you.
Yep. So
I will be needing the electric one soon.
yes, you will be worshiping these formula sheets for the entire semester. Learn to love them.
And another question. So I heard you talking about how in other courses before with Dr. G that you would do thermo, give us a midterm, and then we never talk about it again. But this time, are we actually going to have to remember it since there's only going to be one exam?
I am assuming that you don't need to, because the way it worked last summer is you literally just have the quizzes every single class, and there isn't really much of a final exam. It's just like essentially the final class is just like 3 quizzes you take over the course of an hour and a half, but it's all on the electricity and magnetism and circuits.
Gotcha.
Because it just doesn't really make sense to...
Okay, so basically when the final exam starts to come around, we should just review the quizzes throughout after electricity.
Yes, but double check with Dr. G on that, because I'm assuming he wouldn't change it, because it's worked really well in the past, but it's because the electricity and the magnetism and the circuit stuff is at least somewhat related to each other in terms of you have some equations that like derive further. Like you guys will see, for example, Ampere's law is somewhat similar for magnetism to Gauss's law in electricity, and it's like similar concepts. It's just you have like right hand rules and whatnot in magnetism you don't in electricity, and thermo is just completely different. So
Yeah, it's completely different.
yeah, you don't have to worry about it after tomorrow, I think. So anyway, one more thing.
Let's keep on the side.
Yeah. So one more thing. What is entropy?
Entropy is what heat over temperature.
Yes. And anyone else?
The disorder in a what is it? The disordered in an isolated system.
Yes. And
God.
Roger, you gonna go?
I was going to say about that disorder. Yeah, I got nothing else other than it's with this, the change of the disorder of the system.
So what happens with entropy in, for example, an equilibrium?
In equilibrium, the entropy either increases or stays the same. Is that it?
More
I
specific.
was looking in terms of the second law of thermodynamics.
Yep. And what is that second law?
The amount of disorder in an isolated system either always increases or if the system is in equilibrium stays the same.
Mm-hmm. So basically, in an equilibrium, entropy is at a maximum.
Okay.
And you said it's always increasing or it's staying the same. That's because without any outside forces, no system will ever become less chaotic, if that makes sense. Like, let's think of it this way. An egg is never going to, if you crack the egg, it's never gonna, and the yolk and the egg whites come out, it's never gonna go back in and, recombine, and the shell's gonna uncrack and it's gonna become solid again. That's never gonna happen. And that's sort of everything in the universe follows that rule, where it's always going more towards chaos or disorder. So that's the whole idea of what entropy is. It's sort of confusing. There's like 4 different definitions of it. But the main thing you guys need to know is the change in entropy. You guys might have seen it on your formula sheet. Does he actually have it? Yep. It's the total heat flow over the temperature of a system.
Oh,
and then
total. Write that.
Yeah, so it's the total heat flow over the temperature of the system. And apart from that, you just need to sort of understand the concept of it's a maximum in an equilibrium. Because it's not really something that makes sense. Of all things in this class, it's the thing that makes the least sense in a class of things that don't make sense. Thankfully, you guys don't really have to understand it too much. But let's go ahead and hop into some example problems. We're not going to focus as much on entropy because there isn't really too much you guys need to know about it. You guys might have one question on the quiz tomorrow where it asks you about entropy in a system and if it's like a minimum or a maximum or how entropy changes, and you might be asked to do a simple calculation with the Q over T formula. But the main thing we want to focus on is thermodynamics, cycles, and engines. So let's go ahead and hop into some examples on that. So first example, we're going to have 4 moles of a monatomic ideal gas, and it's going to undergo a 4-step cycle. The first thing is going to isothermally compress from V1 to V2, and then it's going to isochorically do something where the temperature increases from T1 to T2, and it's going to isothermally expand from V2 back to V1, and it's going to isochoric process where the temperature decreases back down from T2 to T1. So the first thing we want to do is we want to actually draw that on a PV diagram so we understand what's happening. And we want to know, does this cycle have a name that you guys might have looked at in this class so far? And what would it be? Let's take 5 minutes, draw the cycle on a PV diagram, and label the temperatures and volumes, and then we'll talk about it. So isothermal compression, isochoric, isothermal expansion, isochoric. If you have any questions, feel free to ask. All right. So, first thing we want to know is, what exactly does this cycle look like on a PV diagram? So, let's go ahead and draw our PV diagram axes. What is our first step of our process going to look like? First of all, what is an isothermal process?
Is when temperature stays constant.
Mm-hmm. And what does that look like on a PV diagram?
It looks like a kind of like a curve.
Mm-hmm. And
It's a curve almost.
what kind of curve does it look like?
A 1 over x curve.
Exactly. It's going to look sort of like a 1 over x. 1 over x looks something like that. So our first step, so let's just go ahead and just draw a sort of 1 over x curve. So is our first step of our cycle, let's draw it more like this. Is the first step of our cycle, which direction is our process going? Our first step here is an isothermal compression. So is it going from left to right or right to left?
If it's a compression, then the volume's decreasing, right?
Mm-hmm.
Yeah, that's why I was confused. I didn't know what direction it was.
It should be going right to left.
Yep, so it's going to go in this direction. So our second step, our second step is an isochoric process where the temperature increases from T1 to T2. What is that going to look like?
It's going to be a straight line going up because it'll be isochoric means when the volume is constant.
Yep, exactly. And you said it was a straight line straight up.
Yeah.
Why is it up?
What is it?
Increase of temperature.
Exactly. So why is it up if the temperature is increasing? What law lets us calculate the temperature based on pressure and volume?
The ideal gas law.
Mm-hmm. Which is? Michelle, you know
PV.
Yeah, I was gonna say the same thing. The ideal gas law, PV equals nRT.
Exactly. PV equals nRT, constant volume, increase in pressure, temperature has to increase. And let's add our arrows to indicate the direction. Then our third step is isothermal expansion from V2 back to V1. So it's going to look something like this. Right? Another 1 over x curve higher up. And once again, obviously going from left to right because it's an expansion. And then the last step, it's another isochoric process. The temperature is decreasing back down to T1. So essentially we're going back and returning to where we started. Does anyone have any questions about this so far?
Nope.
All
Oh
right.
wait, I think I'm still confused on the relationships between like pressure and volume in terms to temperature. Like in my head, I just automatically thought for like B when the temperature increases that like
in its isochoric that it will go up, but
Mm-hmm.
I guess I need a deeper explanation on why that is. Like, I
Mhm.
get it's for the ideal gas law, but I'm still trying to relate it together.
So ideal gas law, obviously we have PV equals nRT.
Yeah.
Right? And so we know it's an isochoric process. So that means volume is staying constant. And then we know the temperature is increasing from T1 to T2.
Yes.
N and R are both constants. N is the number of moles of gas, which we're going to assume is not changing. And then R is our ideal gas constant. So what does that leave for us to make temperature increase while volume stays constant?
It leaves us with pressure.
Exactly. Pressure has to increase to balance the equation. That's why we move. That's why we move upward on our graph. Does that make sense?
Yes, that makes sense now.
All right. And so then, if we wanted to go ahead and label our known values, we have. So we have V2, we have V1, and then we have T1, and we have T2. Right? So, what direction is our energy flow? Actually, first of all, do any of you know what name the cycle has? It's a specific name that at least was covered in the class last year. I don't know if he actually still covers it.
Is it called Carnot?
It's not the Carnot. It's Carnot, not Carnot.
Jeez,
come on.
Okay.
Work on your French pronunciation. Jeez.
Well, see, it's made for seeing a T at the end of it, thinking it is not.
It's Carnot. We don't pronounce the T at the end of words in French for some reason.
Okay.
It's not the Carnot cycle.
Well, then,
is it the auto cycle?
It's not the Otto cycle. Is that the one he covers now? Because he switches us up from semester to semester.
What was the one that... I think it might be in Flip It. Because I think there was a word on there, one of them. I'll start looking.
Does the name Sterling ring any bells?
No.
No.
Nope.
No.
Damn.
No, because the only other cycle I see is the OTTO cycle.
Okay, the auto cycle. So that's changed from previous semesters. But that's fine. So this cycle is called a Stirling cycle. You guys can go ahead and forget that information since it doesn't matter. The reality is, it doesn't really matter. The main one you need to know is Carnot, and even then, I don't really know why it's that important to really know the name of the cycle. As long as you can see the steps on the cycle and understand them and be able to draw them on a PV diagram, that's all that really matters. So for a Stirling cycle, it's isothermal and isochoric processes. For other different types of cycles have different names, but it honestly doesn't really matter. So next thing we want to know is what direction is energy going to be flowing in each step. So for step 1, we'll label these step 1, 2, 3, 4. Is internal energy increasing, decreasing, or staying the same in step 1? How do we calculate the internal energy?
Well, using the first law of thermodynamics. So,
but we don't know anything. We could calculate the work, but we don't know what the heat flow is, so it doesn't really help us.
I believe since it's being compressed, wouldn't work be negative in this case?
Mm-hmm. But do we know anything about... Alright, so we might as well label that now. So we know that work is negative, so work is going into the gas. We can label that.
If work is negative, then according to like the what is it? The first law of thermodynamics. When it's a isothermal process, internal energy is zero. That would mean that the heat would be positive.
Exactly. So why is internal energy zero?
Because the change of temperature is zero.
Exactly. Change temperature is zero, so delta U is zero, and then we know that because the volume is decreasing, work is flowing into the gas. That means Q has to flow out. Now, what about the second step? What's happening in the second step? Is delta U increasing or decreasing?
Let's see. The important thing to note by work is zero since it's isochoric.
Exactly. Work is zero. There's no change in volume.
And let's see. The temperature is increasing, so I would think the heat would be increasing. I think. Because the change in energy equals Q at that point. The heat energy.
Mm-hmm.
So if you know the sign of the heat energy, that's the direction that would be to change the internal energy. So I think it might be increasing.
Mm-hmm. So that's pretty much exactly right. So we know that the delta U is increasing, so essentially delta U, I'm going to use this arrow going in as increasing. And so then we know that the Q also has to be going in to match delta U. And then we know that work is zero. That's how we understand what's going on. So the next step, we have our work. We want to know what our work, our delta U, and our Q is for the third step. We know it's an isothermal process. What does that mean about delta U?
Delta U is zero.
Mm-hmm. And is work in or out?
It's going out of the system at this time.
And why is that?
Expansion.
Exactly. Expansion. And so that means, what is Q doing?
So let's see. That means work would be positive. So Q needs to be negative.
Mm-hmm. Exactly. Q has to be entering. Well, Q has to be entering the system in order to balance out the work going out.
Yeah.
I don't like to think about positives and negatives in this case because it's easier, at least for me, to think about the direction of energy flow.
Okay.
Because we know that delta U is the total change in energy. We have work coming out because it's expanding. So work by the gas is positive. That means there has to be heat entering the gas. And the same thing for the step down here. There's work going in, so Q has to come out. And then we can go ahead and think about the signs of our things. For if Q is positive, it's going in, but if work is positive, it's coming out. So it's sort of it's a little annoying to think about it that way with positives and negatives.
Okay.
In my opinion, if you're able to understand it like that, by all means, go ahead. But for me, I freaking hate it. So the last thing we want to know for step 4, what's happening? It's pretty simple. Is delta U increasing or decreasing?
You said for process 4?
Yep.
For delta U is still zero. No, wait, no.
I was going to say that's for step
Work
1.
is zero.
Work is zero. Mm-hmm.
That means that internal energy. I'm not sure if in this case it will still go into the system or out because.
Well, explain to me what do you understand is going on?
What I understand is that temperature is decreasing.
Mm-hmm. Exactly. Temperature's decreasing, so that means delta U has to be decreasing.
Yeah.
In that case, that means energy is leaving the system. And the energy that's leaving the system, by the first law of thermodynamics, it can't be work. So we know that the energy leaving the system has to be in the form of heat. Does that make sense?
Yes, it does now. I don't know. It was funny when Dr. G was explaining in class. I was so confused, maybe because of how fast it was going. But a real thing I'm realizing is that internal energy is related to temperature. So when temperature goes down, like internal energy goes down.
Exactly.
Okay.
That's the main thing you should know. And then work is related to the volume, right? If the volume increases, work goes out. If the volume decreases, work goes in.
Yes.
So, last thing we want to know is the net work in or out of the gas for the entire cycle from step 1, 2, 3, 4?
Well, by using the areas under the curves, I would think I think there'll be more in a positive work. Sorry to say that again, because the step 3 is higher than step 1.
Exactly. So that means work is moving in or out.
In? Wait. Sorry, it's the other way, I believe. It's out.
Yeah, exactly. Work is moving out. So this cycle is doing net positive work on its outside, which is what most cycles you want to do, right? You want them to power some sort of, you have some sort of like a machinery, like for example a car engine, and you have this cycle that's happening in your car. You know, it's not any specific thermodynamic cycle. It's somewhat similar. You can sort of visualize it like this, but essentially like the gas is like ignited and it causes an increase in temperature. We have some sort of expansion and then a contraction, and expansion, contraction. That's what powers your car. And we have a net positive work moving out because the magnitude, as you said, step 3 is higher than step 1. More area under the curve. Does anyone have any questions about that?
Nope.
All right. And now we do have some values if we wanted to go ahead and calculate things. I'm going to leave that to, if you guys want to do it on your spare time, feel free. Like V1 is 10 liters, V2 is 5 liters, T1 25 degrees Celsius, T2 50 degrees. We could calculate the change in internal energy, heat, and work for each of these 4 steps. The reality is, that's pretty simple. All you guys need to know is understand each step, isothermal, isochoric, and then just plug and chug from these equations down here. You guys will have had plenty of practice with that on Flip It, and you guys will be able to do that no problem on your quiz tomorrow. I hope. Don't fail me.
That's all we have to do, is hopefully do our best.
Do not ruin my trust in you. So, let's go ahead and hop into another example. So we're going to have 6 moles of a diatomic ideal gas. It's going to undergo a 4-step cycle. We're going to have an adiabatic expansion from V1 to V2. The temperature is going to decrease from T1 to T2 during that step. Then we're going to isothermally expand from V2 to V3. We're going to go ahead and adiabatically compress from V3 to V4. Temperature increase from T2 back to T1. And then isothermally compress from V4 back to its initial state at V1. So, let's once ahead, let's go ahead and take 5 minutes. Let's take 10 minutes. We'll draw the PV diagram and then label what direction energy is flowing. So, internal energy, heat, and work for each step, similar to what we've done for the first example. And then we'll go ahead and talk about what kind of cycle it is, and maybe if we have time, we'll go ahead and actually do the calculations for this one. So 10 minutes, and then we'll talk about it.
Dylan, there isn't like a breakout room in like Discord or anything, right? Because I had to just like talk to you about something.
Yep, sure thing. I can move you down to one of the study rooms real quick. We'll be right back, Michelle and Roger. Yep, what do you need? What was your question?
Oh, okay. It's not well. It's actually more of a concern that just recently happened. So did you just hear when I started screaming, "Oh no!" in the middle?
A little bit, and then like your mic cut out.
Okay, yeah. So when I was getting off my bed, my laptop just broke. Yeah.
So, do you like your screen isn't working, or?
No, it's not working. Funny enough, so I had to go and answer someone. So as I was getting off, the bed is really high. My laptop fell off. And I feel like screaming right now because this is my only studying method. And I'm not sure if you remember me, but I'm that girl that is
Yep.
also working at the same time.
Yeah, from the first class, I remember.
Yeah, so I'm trying to figure out what to do in terms of homework. Yes.
Yeah. Yeah, that's interesting. That's a real pickle. I'm pretty sure there's a way you can access Flip It on your phone, as horrible as that sounds to actually do.
It sounds really bad, right? Because I even tried to do it on the phone at work, and it was still really, really hard.
Yeah.
And now do you know if the library at school is still open to rent laptops?
I'm not sure. I would think it would be. I'm pretty sure the library's back open right now. I would send an email and go ahead and ask. Or at the very least, you could go into the library maybe once a week and just get all your Flip It homework for the week done. If that would...
I could try. The laptops are expensive. This is possibly the worst thing that could have happened right now. Yeah, I just wanted to kind of figure out what would be the best way to kind of just do all this work now that my laptop's broken.
Yeah, I mean, the laptop might not. What's probably the issue is just is the top screen completely disconnected from the keyboard, or is it just the screen?
It's not black? Anything's disconnected. It's just now everything is black. It's on, but it's black.
Sounds
wait, I think I see my mouse working. Wait a minute, there might be a miracle.
I was gonna say, I think it's probably just an issue with the display connection, which usually is a pretty quick and usually cheap fix to do. It might run you $50 if that.
I'm gonna hope so, because as you know, I'm working and I'm struggling. I also want to talk about because I low-key am too scared to talk to Dr. G about my situation, because when I talked to him about it, he just said good luck.
All right, so let's go ahead and talk through this problem and sort of try to understand what's going on step by step, similar to the first one. So, first thing we want to know is we want to know what this thing looks like on a PV diagram. Let's go ahead and draw our axes. Pressure, volume. So let's go ahead and go through step by step. First thing we have an adiabatic expansion from V1 to V2. What exactly does that look like? What does an adiabatic process look like on a PV diagram?
I mean, it's also it's a curve, but it's not exactly like when it's isothermal.
Mm-hmm. How is it different to an isothermal curve?
It's steeper than an isothermal curve.
Exactly. So if we have, for example, if we have an isothermal curve, which sort of looks like a 1 over x, our adiabatic curve is going to go ahead and fall faster than our isothermal. So something like this. So let me go ahead and erase that. So that's our first step. We have an adiabatic expansion. So what direction is this curve flowing? what direction is this process flowing? From left to right or right to left?
Right
to left.
Yeah.
I'm sorry, both of you talked at once. I didn't hear either of you.
We said the same thing. It was right to left.
You're saying right to left?
Yeah.
Why is that?
I would think because volume's decreasing.
Is it?
Wait. No, it's increasing. Then it's left to right.
Exactly, it's left to right.
I read it wrong. This is too small.
Yeah, because you're on your phone. But it's an adiabatic expansion, which means volume's increasing. We're going from left to right. So our second step, we have an isothermal expansion. So we're going from V2 to V3. So let's go ahead and actually label these as we go. Move V1, move V2. For our second step, we have an isothermal expansion. So what does an isothermal curve look like?
A 1/x curve.
Which means it's going to sort of fall slower than our adiabatics. It's going to look something like this. It's sort of hard to draw and visualize, but if we were to extend the isothermal curve, it's going to look something like this. So it's going to increase from V2 to V3. Of course, these drawings aren't really to scale, and this might not. It's going to look a bit weird, but we're going to work with it. So our third step, we have an adiabatic compression from V3 to V4, where temperature is going to increase from T2 back up to T1. So what is that going to look like on our curve, on our PV diagram?
Would it be? It would still be the same, like deep curve, but the flow will be going from right to left.
Exactly. It's going to be another steep adiabatic curve. We're going up. It's going to look maybe something like that.
Yeah, going up.
Yeah, and it's going to go up from right to left. And then it's going to end up at some volume V4. And our last step, we have an isothermal compression from V4 back to V1. So essentially it's going to return to the initial state. It's going to look something like that. So does anyone know what this process, what this sort of cycle is called?
It's a Carnot cycle.
Exactly. Hey, Roger, you see how she pronounces it? You hear that, Roger? Yeah.
I'm still going to call it Carnot. I don't care.
Well, your car not correct. Anyway. So yeah, it's a Carnot cycle. It's the adiabatic and isothermal expansions and compressions. This is the main one you need to know, but even then, it doesn't really matter. So next thing we want to know is what direction is energy going to be flowing for each step? So let's start with the first step. We'll have 1, 2, 3, 4. Is internal energy increasing or decreasing for our first step?
I believe it's increasing.
Why would it be increasing?
It could. Well, first of all, I'm going to definitely say heat is going to be 0 in this case because it's aerobatic.
Yeah.
And then second, it is expanding, so work will be negative in this case, or at least going into the graph. I believe I'm getting all that correct.
Not quite.
Okay,
You're getting things mixed up because you're thinking about positives and negatives. But let's think about it. You said that the graph was expanding. So what does that mean for work?
Shouldn't work be going in?
Not quite. Think of it this way. We have a balloon.
Oh, dang it, it's expanding, going out.
Exactly.
Okay, I see. All right.
Yeah.
not necessarily mixing up positive and negatives. I mixed up the which one's going in and out.
Yeah. So work is going to be out of the gas. Like imagine a balloon is expanding. It's going to push outward on all the air surrounding it. So work is out. So what does that mean about internal energy? Is it positive or negative?
In this case, it's going to be, I believe, it's supposed to be negative because delta U is supposed to equal negative work by.
Exactly. Or another way, is there another way we could think about it? Michelle, you want to chime in?
I was actually gonna say the same thing as Roger.
Okay. But is there another way we can think about why delta U would be negative?
I'm not sure.
Think about the temperature. What's happening to the temperature?
The temperature is decreasing.
Exactly. So delta U has to decrease.
Okay, yeah.
Because delta U is equal to, we'll say 3/2. In this case, it's actually 5/2 because it's a diatomic gas, but it doesn't really matter. I'll write 3/2 up here. We have N, K, B. God, I can't draw B. And then we have delta T. So it's a function of delta T. And then, as we said, adiabatic, there's no heat flow. What about step 2? Is work in or out? What's happening to the volume?
Volume's increasing.
Mm-hmm.
And it's expanding too, so it should be going up.
I'm just drawing the arrows, then I'm going to label which is which.
Okay, I do believe it's supposed to go out because it's also expanding.
Exactly. Work is out, is expanding. So what does that mean about heat flow? Where does Q go?
Heat flow is going in on Q.
Exactly. And so what's happening to the total internal energy?
It's 0.
0. Exactly. No change in temperature. Third step, adiabatic compression. We would expect that it's going to be, because volume's decreasing, what direction is the work going?
As volume decreases, that means work is decreasing.
Exactly. Work is going into the gas.
To the second.
So that means delta U has to be going into the gas because there's a total increase in internal energy to accommodate the work because there's no heat flow. And then the last step, like we mentioned earlier, we have an isothermal compression. Isothermal, there's no change in internal energy because it's a compression. Work is going in and heat flow is coming out. Does that make sense? Anyone have any questions?
No question.
I only messed up the direction it went through. Honestly, I actually did all the correct work, but I messed up the direction. Kind of made it more of. I made it clockwise instead of counterclockwise.
Oh, okay. Yeah, that makes sense.
I made engine instead of refrigerator. That's what.
So, like you're saying, so you just mentioned, is the net work going in or out of the gas?
Into?
Exactly. And why is that?
Yeah.
It's gonna sound funny, but the reason why I thought of it because the last one that we did was clockwise, and that was going out, and then this one is the opposite direction. So I thought the other thing.
Well, I'll be totally honest. That would absolutely work on a quiz. Because it's a quiz where it just matters if you're right or wrong, and in this case, you're right. Anyone have any other explanation, though?
I believe it's because again it's work under the curves, and from the final step 4 to 1, the work is going in.
Yep, exactly. Larger area under the curve for work going in than work coming out. Because the area under the curve for work going out is just this area under here. Versus for work going in, it's the area underneath plus all the stuff inside as well.
But heck, the other explanation is much easier to say and still understandable.
Exactly. But if you were wrong about the first problem on a quiz, then you'd be wrong on this one as well.
Yeah. Yeah.
Boom. Anyway, anyone have any last questions about this?
So
I don't.
I'm trying to figure out the network thing. So it depends on which processes has like more work like going into it to figure out if it's going like out or into the gas.
Yeah, so it's about so the area under the curve is the work, remember, right?
Yes.
And so for the processes going where it's expanding, which means work is going out, the only area under the curve is the stuff under here. Meanwhile, for our two processes where we're going back in, so work is entering the gas, the area under the curve is the area within our cycle plus the area down here as well. So it's a greater area under the curve.
Oh. Okay. And would it matter like so the systems for like a refrigerator or a heat pump?
Mm-hmm.
Would it tell us like are we supposed to like assume and know what kind of processes are in those type of systems?
Well, like a Carnot versus an auto cycle versus other stuff?
Yeah, like am I supposed to like
Doesn't
if
matter.
let's say he gets a question saying there's like a heat pump or a refrigerator, and am I supposed to know?
Well, you would be expected to understand what direction the cycle would travel in. So,
Gotcha.
What direction would a heat pump be? Clockwise or counterclockwise?
Counterclockwise?
Why is that?
I would think that for a heat pump that stuff like such as work would be going into the system.
Exactly. And what about a refrigerator? Clockwise or counterclockwise?
That would be clockwise.
Not quite.
Not quite. See, I'm still confused on like what directions each of them are supposed to be.
So a refrigerator and a heat pump would have to be counterclockwise because they need work coming in to power them.
Ah.
Meanwhile, a heat engine would have to be clockwise because the whole point of a heat engine is we want the work coming out. So we want more work coming out than goes in.
Okay, now it makes sense.
Right. If that's it for questions, I'm going to go ahead and wrap up the session. Once again, we didn't quite have time to actually do any calculations, but the calculations are pretty simple, and you guys get plenty of practice with that on your Flip It and in the class questions. So, that's it. I'm going to go ahead and wrap it up. Thanks for coming, guys. Hope this helped out.
Thank you.
Thank you. Have a good day.
Good luck on your quiz tomorrow, and then we'll go ahead and start with electricity. And that's going to be real fun.
Exciting.
Yay, trigonometry. I already saw.
Yeah, there's a lot of trigonometry for the first part, but after that it gets simplified.
No. Okay.
All right. Thanks for coming. I'll see you around.
Thank you. Bye.
Bye.
Goodbye.